Right. Professor, being a professor is so lucrative.
Go to the casino. Yeah, let's do one. College professor? Principal professor. And a parent. Who's an education lead? 1, 2, 3, 4, 5.
I love it. It's so much fun.
Who's a communication major? 2, 3. Who's nursing? Who's in home?
Yeah.
Really
I
don't.
hate the bottom.
B.
B. And I was like, no, what B are we playing here?
Why are we talking about
It's a paper B for an art project. Walk on
that?
a.
Makes me smile. I don't like 2, B, 3.
Like B. What do you write my own shapes?
That's so beautiful.
All right.
I get so much.
Hi, guys.
Hi.
Okay.
You want that both of those?
Whatever.
It was really nice.
Want to do it's fine. So I had a question about some homework. 6:18. But I'd start today talking about that. I'll make this comment about me not being heard. All right. So some homeworks. So I'll try, first of all, I'll try to get take home written, I'll say by Monday or Wednesday next week, and or not a homework, take home. And I'll give you about a week, like 5 days or something, to do it. So just depends on how much I can get done this weekend. I'd like it to be ready by Monday, but we'll see. Okay, so one person asked about problem number 6. This is chapter 8. 6. So let me see. I don't know what's going on. All right. So there's some graph in the book, which I will try to replicate here. Let's see, 1, 2, 5, 6, 7, 8. Something like that. So you guys can tell me if I get something wrong. Very likely. This. Here. And okay. So for two, something like this. All right, let's see. Did I get it right? First. Okay. So it's A, B, C, so it's clockwise. So I don't know why anybody would ever orient anything clockwise, including the makers of clocks, but they do. So anyway, this is not the way mathematicians. All right. So this is the graph. And there's some questions about it. This is problem number 6. So let's do them. And I think that there was a point raised last time. I didn't really talk too much about things like this. So that's fine. And it's totally fair game to ask about these questions. So the first question is 6A, is find all cycles of length 2. Okay, so what do people?
Need one more from A to B.
Oh, do I? Well, thank you. From A to B?
D.
D. Ah, perfect. Thank you. I deleted one of these. Thank you. Just to make it look a little less messy. Thanks. All right. Great. And all right, so let's take these one at a time. So for A, what do people have to say? You're finding cycle length 2. Now, directed graphs. So a cycle is like, a circuit, but for a directed graph. So you want to be going in order. You don't want to direction of edge. E to B, right? E to B. So if I go E to B, and I don't know, I mean, you could do this if you wanted. If you just wrote EB, I would probably be happy, but this is, I know what you're talking about. Any others? Yes, no? Why not? Why aren't there any others? Right, so the length of 2, so if I start somewhere and I go somewhere, for it to be length 2, I need to go back to where I started. So there's only one pair of vertices or nodes that have 2 edges between them, and that's B and E. So this, and since they're directed in the right way, it's not a multiple edge. You're good. All right, so this is it. B. Length, same question, but now length 3. Point cycles of length 3. Okay. Now, you guys, all right, so question, what do people think? Okay, you said what? E? A-E-B, good. A-E-B, that looks like a cycle. I'll just wrap it up. Again, I don't think you necessarily, I don't know if the book puts this last. And others? Are there others? Why are you saying no?
Because you can't go to C because it doesn't go out.
Right.
And B, it just goes to C.
So C is what's known as a terminal point. Everything that goes into C, once you're there, you're stuck. C is a terminal, so there's not going to be any cycle through C. because you have to be able to leave in cycles. And so you can imagine just kind of, killing everything going to C, nothing will go through it. Now, if you look at the graph, D is now a terminal point. Right? Nothing's going to go through that. And then you're left with this. And there's only one cycle of like 3. Okay, so now cycles of length 4. Same logic we just gave applies applies for any cycles, right? So in particular, length 4 as well. We can't go through C and can't go through D. So we're just left with these 3 vertices, 3 nodes. Is there a cycle of length 4 here? Not really. You might think, well, I could use these 2, but you're going to have to increase whatever cycle length you have by 2. And so it's going to be odd degree. And cycles, well, okay, I believe cycles aren't allowed to repeat. I mean, you could, I guess, imagine EB. I don't know. You'd have to, I think that's, you don't want repetition for cycles. Double check, but if you're allowed to repeat, you could do this twice, but I don't think you're allowed. I think this book. So graph theory is filled with different definitions. People will use the same word and mean different things depending on what book you have. So I'm just saying that to not to say, okay, things are confusing, but in this kind of subject, people use different definitions. So I'd have to look at the books. I think the book, since they don't want paths or circuit to repeat, I don't think they want cycles to repeat. All right, so I'm going to say none here. That's the answer. If you're ever unsure about something like that, and you want, it's always good to clarify when you're doing a homework. So when I look at these homeworks, look at them, sadly. You can, it's nice to see that you guys are, you have a reason for why you're doing it. So you can say because no repetition. So. All right, so the other one was 16, was asked about, which looks like a lot of words. 8, oh, was it 18? Also a lot of words. Okay. I guess it was 18. My memory is not good here. So let's say number 18. Thanks for the confidence. Okay, so the diagraph in this figure, which is very similar to what I've drawn, but I'll have to make some changes. So let's take a look here. So this one only does not have a multiple edge here, and does look like it has one extra edge. So I'm going to have to reverse some directions. All right, give me a second, guys. So go this way. Both of these guys go in the opposite direction. Fun. Sorry, I didn't really prepare this. I should have prepared. Okay, that's good. That's good. That's good. Not good. All right. That looks good. That's good. Okay, I think this is the graph. All right, so this is an example of tournament diagraph. In this example, the vertices of the diagraph represent 5 volleyball teams in round robin tournament. An arc represents that X defeated Y. So XY. So for example, This means that team E defeated team A. Okay, so now the first question is which team won the tournament? One? Whoa, one? Okay.
Do we need to teach the class?
Huh? Yeah, you can, please, by all means. You know, children are taxing on your brain. So
Wait, your
most-
kids or us
Yeah.
kids?
I'll leave that to you. No, both children. No, my children. You guys are great. Wonderful relief. So I assume the team that won is probably the team that won the most games, right? So, I know this is like deep stuff here. So based on what we've learned about what this diagraph represents, we would look for a team that's the initial point of as many arcs as we can find. So can you guys tell me then? By looking at the graph. So if I look at B, I can say, okay, well, B won against beat A because I've got that arrow. B beat D because I got that arrow. But B lost to C and E. Because, okay? E, right. E is like everything's going away from me. Like a winner. Everyone runs away. All right, good. So there you go. He wins against. I mean, so this is not like not questionable. I guess some round robins, you win everything, but you still win. All right. B. So who would be the worst choice to be the? No, wrong question. Which team came in last in the tournament? So which lost? Which came last? And everyone says A because, yeah, A looks very sad. A lost. All right, suppose that you're given the tournament diagraph of some tournament. What does the in degree of a vertex represent? And what does the out degree represent? Sorry, guys, you have to speak up. What? Okay, well, let's be specific though. In degree. Okay. In degree is, well, lost. What does it mean? Lost. That's a word.
Lost a game.
Lost a game. That's true too. That's several words. So in degree. What is the in degree of? Hold on. Let's say I look at B. What is the in degree or D? Let's say I look at D. What is the in degree of D? 2. So I say 2 lost. So the in degree is a number. It's number 2 in this case. And it represents lost. No, it represents what? Well, okay. So these are nouns, but is 2 failure or is 2 something? I mean, if you say 2 is failure, every time you use the 2, like I have 2 failures because I have 2, my kids are failures. So I have 2 of them, right? Which, I don't think so. I think it's great. But like every time you use the number 2, you're saying that's failure. No, it's not failure. It's what? Our loss. Okay. I'm trying to say, okay, the in degree represents what? What is the in degree? What is the in degree? Like its essence. Looking for a specific. Okay, good. But if I say the in degree is this of a graph of a diagraph, what am I telling you? What is it? What am I going to give you? I'm going to give you. No, I'm not asking for the meaning. I'm saying, what do I give you? What do I give you guys? What is it that I give you?
A trophy. I don't know.
Do I give you a trophy? Really? What if the graph is like the World Wide Web? Do I give you a trophy?
Emotional distress.
I'm feeling it. How do I want you guys to come to this. Huh?
A fee.
Not this particular graph. I'm just saying, if I have a graph, a diagraph, and I say, here's a vertex, and I say, the in degree of this vertex is this, what is the this? What is the this as a thing?
A number.
A number. Thank you. Oh my gosh. Thank you so much. All right, you got an A in the course. You can right. A number. It's a number. So it's totally impartial. It has no adjectives attached to it. It's a number. It's
See?
you could have, but you just weren't. So, all right, so you did, but now we've got it. It's a number. That's what the in degree is. So it's not loss, it's the number of losses, right? It's the number
Okay.
of losses.
You just said that. Okay, we're just-
Right. Okay, so from that perspective, now what is the algebra? The
Win.
number of wins. Great. Thanks, guys. Sorry about that. Oh. Okay, we're going to do it now. If T denotes the tournament diagraph of a round robin tournament with n teams, then for any vertex x in T, the in degree of x plus the out degree of x equaling n minus 1, or wait, sorry, the in degree of x plus the out degree of x is equal to n minus 1. Okay. So why is it true? So did people, that was kind of read quickly. So it says, suppose, so T represents tournament, round robin, tournament, with n teams, capital N. Then they basically are saying, why is the following equation true? That the in degree of a given vertex x plus the out degree of x is equal to n minus 1 for any vertex. I don't know, we can say let's say vertex. So why is it true?
They don't play themselves. Is that wrong?
No, it's right, but give me a little more than that. So they don't play themselves, but and they play what?
4 games.
Four?
It's always gonna equal 4.
Okay, for n, we've got n. So we've got n teams. You're right in this, for this example, you will be right. So, but let's do the general setting. So n, but you're right. I mean, so go on with it.
There's no ties. It has to be-
That's a part of this. So that's actually, if you look in the book, that is actually a part of the requirements to make one of these diagraphs for a tournament, that you can't have a game where you have ties. So that's true. But, and so that's also a good point. But let's assume that there are no ties. So going in with that knowledge.
So then the line doesn't go back to itself.
So you said they didn't play themselves, but who do they play? Let me ask that. And how many other teams are there? So there are n teams altogether, and they're one team. How many other teams are there? N, and not 5.
Oh.
How many? If there's just n teams, how many teams are there? N minus 1, right? Take away themselves, and they're n minus 1 other team. So they have to play all of the other teams in a round robin. You play each of the other teams. So that's why. So they have to win or lose to every other team, and each win or loss will be accounted for in the in degree of the out degree actually vice versa. So that's an explanation. I'm not going to write that down. Take it as like. Hey guys, how's it feel? Feel better? Yep. No, you shouldn't feel stupid at all. So yeah, like my daughter yesterday, she's 9. She plays chess tournaments, right? And she plays online, chess.com, and she's gotten like the habit of playing around me. I kind of help her here and there. Not like tell her what to move, but give her advice. But she got addicted to it. And then last night I'm like, okay, go play a game without me. And we had like a 30-minute like cry session. But she doesn't want to like disappoint me or lose. I'm like, you're gonna lose. And I'm like, watch, I'll lose. So I played like quick game. Like that. You guys, but the point is, look, when you're the point, I'm not trying to tell you a story about my daughter. I'm just saying, like, don't cry, first of all. Second of all, like, you're not dumb when you don't know something. You're learning it, right? This is just, you're learning it. I'm sorry, and I don't mean to make people feel bad or stupid at all. I'm sorry.
I had a question about another one.
Another one. Okay.
So you don't have to explain it. I just didn't know if for 40, we were looking at the diagraph, if A and B still had to be before D. Or I could just go off of the priority list.
Sorry, 834. Okay. So this will be good. We're going to do some of the priority list stuff. So we should. You're asking.
Like on the actual figure, A and B are before D.
Yes.
And I didn't know if it had to be before D for the
On.
new priority list.
So that's a good question, and the answer is no, it doesn't, and it's confusing. And the point is what you're doing is you're not. So it's the question that you're asking is a very good question about how you deal with priority lists and schedules, how you make a schedule from a priority list. And the point is that what you don't look at is the priority list isn't something you kind of go down and do each task one at a time. That's not the way the priority list works, because there are these precedence relations that get in the way of you doing it that way. Instead, what you do is you actually go down the schedule. And so at any time, you look at if there's a processor that's available. If it's available, then you go down for that particular processor, maybe choose one. If there are multiple ones available. You go down the priority list and you see the first ready one. So it may not be in the beginning, there may be a lot of ineligible ones, and then you get to it, and then you put that in. So that's how the priority list works with schedules. So you can give any permutation of the tasks that you want and make a schedule. Their priority lists are free to be whatever they want. Make sense?
A and B matter if it's before D.
The A and B matter.
Like you have to use the figure.
Yes. You have to use the figure when you're making the schedule. Is that what I'm? Yeah. It's a question. The figure will tell you whether certain tasks are eligible. Maybe we'll see this in just a second. I was going to start with one. With a decrease. So okay, let me start the lecture now that I'm over halfway through class. Okay, we've got time. So there's this, what is it, decreasing time algorithm. So what we want to do, what our goal is for the rest of this chapter, is to give ourselves ways of creating schedules. And the way we're going to create a schedule is by writing a priority list. And so all of the algorithms are sort of geared towards writing down a priority list. And the first one is really silly, called the decreasing time algorithm. Although it sometimes works just fine. So what do you do for the decreasing time algorithm? Well, you look at your tasks, so all my tasks, I've put all my tasks here. And, or you can look at them as nodes in this diagraph, precedence relations. And then you want to make a priority list. The priority list is an ordered version of these guys. And for the decreasing time algorithm, you just want to make sure that you're ordering them according to how long they take the test. The idea is you finish the longest tasks first. Kind of a simple, and if there are multiple tasks at the same time, you can just order them however you like. So for this example, you guys can tell me how I can order these tasks A through H. So here's, I'm going to write my priority list. You guys can tell me. Tell me what I can write here. What's the first? So given what I just said, what's the first task that I can write on this list? So should I repeat what I said, kind of? Okay. So what I said is, what is the priority list first? Priority list is an ordered list of tasks. So here, I have a list of tasks. Right? And it's sort of ordered alphabetically, I guess, but it's just a list. We want to give it a different order according to decreasing time. In other words, we're going to start with the task that takes the longest time, then the next longest time, and so on. If they're ties, we can order them however we like, the ones that are tied. Okay, so if I'm going to do that, what can I start with? C, sure. And I'll write the time in just for clarity. What's next? H, great. Now, B. E. B. And then I've got the last three, A, B, and F, let's say. Great, I've made a priority list. Okay. Now, one thing you'll recognize about this list is that some of them need to be done before others. So for example, A here is going to have to be done before D, based on my precedence, my graph here, right? I need to do A in order to do D. And A is way down this list. It does come before D, so maybe that's not the best example. Let me do D and G. D here come before. Of course, D in my priority list is after G. That doesn't matter. That doesn't matter. We can still make the schedule. All right, so let's make the schedule now. So how do we make the schedule from the priority list? Again, we look at the times. Whenever something becomes available, that's when we start looking at what we do. So right at time 0, everyone's available. All 3 of my processors are available. So I'll take my first processor and I'm going to assign it a task. And the idea is to go down this list and find the first ready task. So C is ready, pardon me, C is ready. Because C, I have nothing except starting time. So I can definitely do C for processor. C's ready. So I did that, and I like to cross off so I don't forget. Now, I'm still at time 0 because I have 2 other processors that have not been assigned tasks. So I go down my list for processor 2, and I see H, but H does require E to be finished, so it's not ready. And so I have to skip H and go to the next one. B is ready, so I can assign B. Off. Again, I'm still at time 0 because I've got a free processor. So processor 3 is available. So I'll make an assignment. H is still ineligible. E needs B and C to be done. So at time 0, it's not eligible. So the only thing, actually, you guys can tell me, what is the only thing that is eligible? So this is not eligible. Right, this is not eligible. This is not eligible. A is the only thing, the first ready task. It's language. So I'll assign A. So now I've assigned tasks to all available processors at time 0. So I go up to the next time. And the next time is time 1. These guys are busy, can't assign anything to them. So processor 3, I could assign something, but can I assign something? Okay, so well, at time 1, that's the question. At time 1, the only task that's been completed by time 1 is A. And all of the other tasks require other early, have precedence relations with things besides A. So D requires B, for example. So at time 1, I have no ready tasks, so I have to wait. So this guy will be idle at least until time 2. I go to time 2, and now I've got 2 processors ready, and A and B tasks have been completed. So I can make the assignment of D. That's the only task that's available. So, or that's ready, so that I'll make that assignment. Sorry, I forgot to cross off A. Now I'll cross off B. I'll assign that to processor. And again, this guy has to be idle because. So now, at time 3, all 3 of our processors are available. We go down the list and we ask, is H ready? No. E ready? Yes. So E is ready, but H is not ready. So we'll assign E +1. And now we're still in time 3 for processors 2 and 3. We have to look and see 2 and 3 if they're ready, if there's anything ready. So if I look at H is not ready because E is not complete. G is not ready because E is not complete. And F is not ready because, actually, F is ready, pardon me. F is ready. F is ready, so we can assign. So that will be idle, because nothing else is ready, TH or not. All right, now we can move to this time 4. Our processor 2 is available. Can I make any assignments? Last 2 things tasks that I need to complete are H and G, and both of those require E to be completed. And E is not completed at time 4. So I have to move on, and then I will be able to assign the task, and I'll assign H first. And then I'll assign G. But you'll see, each time, so if each time I kind of move up in time, I should write like idle or something like that, so that I'm actually kind of filling in my schedule as I go up in time. Does that help clarify how this works? Great. Now, this particular example, it turns out that we get an optimal solution. So this example, this is an optimal schedule, but it turns out, and we'll see it probably next lecture, that this is not the best algorithm. It's kind of the easiest. It's not the one that you will often not get an optimal schedule if you use this algorithm. So it's not just an approximate algorithm. doesn't do a good job of getting you close most of the time. This time it's just happened to be okay. So for example, yeah, let's actually do that. We can do it now. So let's do this. We'll do the decreasing time algorithm again, but we'll do it with this example. Yeah, it's a little simpler. I changed a little bit of the times around for this. Time. So let's see if we can do this decreasing time algorithm for this guy. It's the same kind of setup as we had last lecture, the lecture before, where we've assigned an introduction and 2 chapters and a bibliography. I've just changed the time that it takes to do these tasks. So the introduction takes longer now. So now if we write down our priority list, what are we going to write down? What's the first item, first task? This case. Introduction, right? It takes the longest. In this assignment, this is going to take the longest. Then the second chapter is going to take the longest. It's 4. And the first chapter. And a bibliography. Not so many tasks, but we can write them down. So now we have 2 students. And all right, so you have to assign, the introduction really doesn't require anything. So we can assign it. So we'll assign it to the first student. And then the second student's free, so we can assign something to that student. Namely the second chapter, because that's the next thing on our priority list. So we'll do that. And now, I don't know why that happened. And now we're on to the chapter 1, and we're at time 4. So time 4, chapter 1 doesn't require anything, so we can assign chapter 1 to the student number 2. And now at time 5, student 1 is available. However, at time 5, student 1 has to wait, because in order to do the bibliography, these chapters both need to be completed. So at time 5, we need to have some idle time, and at time 6. And then only then can we, once the chapters are completed, can we schedule the bibliography. And this is too long. The schedule, as you can see, is 10 hours. You can do better than that. So what we will do is find another algorithm that allows us to make a priority list that makes this more efficient. Wow. Questions?
So I'm not quite understanding where it's being idle.
Why there's idle time? Yeah. Okay, good. So, okay, before I brought this guy over, before I scheduled the bibliography, I looked at time 5, and I said, okay, this student 1 is available to do something. And the only task that was left at that time was the bibliography. But now, and this is a question earlier, when you're using the priority list to make the schedule, you have to consult your precedence graph or your diagram. So I know the only thing available here is the bibliography. So I look at it and I say, okay, these arrows represent precedence relations. In other words, these need to be completed before I can do this. My schedule, and I say, okay, well, these are not completed yet at this time. So I need to wait until they're completed, and then I can schedule that bibliography. Make sense? Everyone with me? Okay. It is, I mean, it's a pretty rich model, actually. I mean, it's got like 3 different things going on. So it's not like, it's kind of fun. I'm not saying I do it in my spare time, but fun for me. I mean, guys, math is beautiful. This is not something I would say is a beautiful thing in math. I'm sorry, it's really sad. I'd like to show you beautiful math. But in my experience, whenever I show students beautiful math, it's not like something they like very much. I always get the question, how do you use this? I don't know how to answer that. I get really angry when I answer that question, but not in this class. This class is all about that. It's okay to ask. All right. Questions? Huh?
My brain is.
Your brain's Friday. Yeah, it's Friday. It's Brain Friday. So so the idea is, let's find a better way. Let's find an algorithm that will allow us to schedule make a priority list that is not as bad as this one. And for that, we have this critical path algorithm. It's kind of neat. So how do you do this? Well, first thing I need to tell you about is what is a critical path. So a critical path I'll just call it a task diagraph. I don't know what they call it. They call it something else. Precedence diagram. I don't know. I'll say one of these diagraphs we get from this, making the schedule, precedence relations. Starting at a vertex X, is the longest path from X to N. Longest. How do you measure longest? You measure it not in terms of the length of the path, but in terms of the processing times. I'll say in terms of your longest means longest time. It's a little confusing, but this is what I mean by longest. So how do you, so let's give an example. I'll go up to this guy. Take a look at this guy. I don't think I'm going to have time for this, so I'll just get rid of it. Okay. Good example. So if I look at A, let's look at B instead. If I look at B, I've got a lot of different paths to get to N. I can go here, I can go here, go here, and go here, right? There's a lot of different ways I can go from B to the ending point. So what does longest mean here? It means that if I take this path, for example, I can look at the total processing time it takes. It takes 2 hours, say, to complete B, 1 to complete D, 1 to complete F. So 2 plus 1 plus 1 is 4. So that's the processing time along that path. So I want to find the path that has the longest one. So what do you guys think I should choose here? Where should I go from B? B to E. Correct, right? And I'll get a length 7. 3 plus 2 plus 2. That's the critical path starting at B. So, path. just gonna write it down, and then I think we'll finish. So next time what we'll do is we'll find that how to find critical paths in general, what the procedure is, and then we'll use that to write down a priority list. All right, guys, have a good weekend. It's been a blast as always.